Hey, Alex, it's Christian. Hey, great questions. And this is kind of a nice lab. You've done a great job on it, and I added just a few things to it. First thing that you'll want to see is here's your mass. So this one was for, the one with the bigger surface area. And I think this one was the one with the smaller surface area. So I'm just going to put big, and then I'm going to put small here. So that's your data. I added weight. So what I'm going to do is if you had your block and I make a dot for it, pointing straight down would be the weight. So that's mass times gravity for your block. And then straight up, equal and opposite would be your normal force. So if you think about if you had that block sitting on a surface, sorry about that, and then you grabbed a hold and you pulled the block this way, and you know the mass of the block and you know how much force you pulled it with, uh, when it first starts to move, okay, so the force to move is right here, and then the normal force, I plotted it here. And what you find out is as your normal force or the weight of the block goes up, the force to move goes up, and it's a linear relationship. So you'll see the straight line here. So let's go back to this guy. I know that the force of friction is in this direction. So this is the force of friction, and then this is that force of that pull that you did. And so that's the force to move. And we know that this and this are in opposite directions. And when this gets big enough, this continues to get bigger. And then when this is just a little bit bigger than this one, it starts to move. And that's what you were plotting here. So let's think about the next thing. The force of friction is equal to this funny symbol here called mu, or the coefficient of friction, times the normal force. And this coefficient of friction tells you basically how sticky the surface is, or how hard it is to slide. And so when you pull on it and then it gives you these dots, you can plot the force to move, which is the force of friction, and then the normal force, which is this guy, and the number that you see right here is measured in newtons over newtons, so there's no unit, but this is what we call the coefficient of friction. And the bigger it is, the harder it is to move something. So I did that, and then I did it again by plotting the weight on the bottom and then the force to move at a constant velocity. So when these two are equal and it's moving at a constant velocity, I'll do this in blue. So when it's moving at a constant velocity in this direction, these two forces have to be equal to each other. So the force of the pull is equal to the force of friction, and that's at a constant velocity. This one over here, so this is the coefficient of static friction, and this is the coefficient, so our slope right here would be the coefficient, so coefficient of kinetic friction. So kinetic and sliding friction are the same, and then static is where you're not sliding. So when I look at this, this number should be smaller than this one because this coefficient of static friction, it takes more force in order to get something going than it does to keep it moving. So that's the first one. On the second one, you get the same type of trend. So you'll notice that the weight, when I plot the weight, and the force to move, so when I plot these two, I get this graph. And this is also 0.558. It's a little bit smaller. I actually used your numbers that you had crossed out because you really do need those. And you'll notice that on the smaller surface area, you really didn't get too much of a change. It went from 0.561 to 0.558, so it didn't really affect that. This data probably isn't as good. The way I know data is good is by looking at these numbers. So these numbers will tell us how good your data is. And we want it to be close to 99 or almost 1. And so all these three are really good. This one I'm not sure might be as significant. So you'll see this is only about 93%. So probably somewhere there's a little bit of error. If I get rid of this dot and replot it, then I get a bigger number here. But you'll notice that this one and this one really aren't comparable. So it looks like in sliding friction that your smaller surface area didn't provide as much friction. So this is a really small number here. Ideally, if you didn't have any change, okay, so if surface area didn't matter, then your numbers would all four be pretty much the same, and that might be kind of what he's going for. If we go to the previous question, it says, would your results change if you had two containers with the same surface textures being pulled in tandem? And no, it would have you would have to use more force because there would be more weight, but the slope would be the same. So for the third question, your slope would be the same, and that's the only thing that would stay the same. Your numbers would be bigger for each one, but your slope would stay the same. Fs and Fk. Fs, remember, is static friction. So this is static friction. And this is the friction you have to overcome to move something. Okay, so if you've ever pushed a box and it's hard to push and all of a sudden it gives way, that was static friction that was keeping it from moving. The minute it starts to slide, that's kinetic friction. So this is kinetic friction, and this is to continue, and I'm going to put to slide. So this is, you're going to overcome friction, and really, I said to move, it's really overcoming friction to slide. So moving, I always like the word sliding because that's much better. This one is just to continue to slide. So that is the difference. Hopefully that helps.